Hydrochloric acid and sodium hydroxide are examples of strong acids and bases. Their dissociation constants are so large that we can assume that 100% of everything that we put into solution is dissociated at equilibrium. That means that the concentration of hydronium in the aqueous HCl solution is equal to the amount of HCl added per liter. So for example, if we added 0.005 moles of HCl in 1 liter of water, that would produce 0.005 molar solution. We regularly interact with weak acids and bases too, often enough that we come equipped with our own sensor. What we taste as sour is a measure of the concentration of hydronium in a solution. The right amount of hydronium in foods is a delight. Here I've collected a few examples that were convenient around my kitchen, with some lactic acid, some citric acid, oleic acid in olive oil, acetic acid in the vinegars and ketchups. Really, we're surrounded by a universe of weak acids and bases. Weak acids and bases do not dissociate completely. Their dissociation constants, Ka or Kb, are much lower, and they become important to calculate the final concentration of hydronium in a solution. Let's take lactic acid as an example. The lactic acid molecule gives a hydrogen ion to water, meaning that the lactic acid acts as an Arrhenius acid, and water is acting as a base, by taking the hydrogen. But in reality, the reverse reaction is also occurring at almost the same rate. That lactic acid's conjugate base, lactate, takes the hydrogen from hydronium to make lactic acid and water. The equilibrium dissociation constant for this reaction is 1.4 times 10 to the negative 4. That means that the concentration of lactate times the concentration of hydronium divided by the concentration of lactic acid is equal to 1.4 times 10 to the negative 4 at equilibrium. Where did the water go in this equation? Well, because it's a solvent, we don't really think of it as having a concentration in itself. Water is not included in the calculation, only the molecules dissolved in it. So if we add a small amount of lactic acid to 1 liter of water, what's the final concentration of hydronium? Let's lay out the problem step by step. We start by adding 4.0 times 10 to the negative 5 moles of lactic acid to 1 liter of water. A certain amount of that is going to react with the water, so we'll lose X amount from the amount of lactic acid. According to our balanced equation, that same amount will become hydronium and lactate. In the end, we're left with all the concentrations in terms of one unknown, we'll call X. We can then rewrite the equilibrium equation as X times X divided by 4.0 times 10 to the negative 5 minus X equals 1.4 times 10 to the negative 4, which we can then solve as a quadratic equation, meaning that the concentration of hydronium in this solution is 3.25 times 10 to the negative 5 molar. Remember the question we left unanswered in the last video, whether bicarbonate would act as an acid or a base in ammonia solution. To answer that, we need to determine the relative strengths of the conjugate acids of all of the different ions in solution. How readily each one is going to give up its proton will determine its reaction rate, and that's going to judge which way is going to be faster at equilibrium. So if we write down the acid dissociation constant for carbonic acid and for ammonium, we can see that carbonic acid is the stronger acid. If we look at the base dissociation constant, the equilibrium constant for the conjugate bases, we find that bicarbonate is a weaker base than ammonia. So the stronger conjugate acid is the weaker conjugate base, and vice versa. That's a useful rule to remember, and one that means that equilibrium will favor the weaker set of acid and base since their reaction rate is slower. So it's not really a simple question of either or, but it's both. We can see that we would end up with a solution in equilibrium between all the possible combinations of ammonia and ammonium, carbonate, bicarbonate, and carbonic acid. Finally, let's take a quick look at the self-ionization rate of water. Since water is the only reactant and it's not included in the calculation, the constant that we'll call Kw is equal to the concentration of hydronium times the concentration of hydroxide. And experimentally, we find that the amount of each in neutral water is 1.0 times 10 to the negative 7. So the dissociation constant of water is 1.0 times 10 to the negative 14, a fact that will become handy in the next video.